So I was going to talk about non-linear systems of differential equations today, because you definitely started to cover that in class. Non-linear systems of differential equations. And I would say there's kind of three pieces to this. In fact, let's write them down instead of just saying them. There's finding equilibria. There's the linearization. And then there's classifying equilibria. So whether you can just let that out. So classifying meaning, is it going to be a stable node, an unstable node, a saddle, a stable spiral, an unstable spiral, or a neutral spiral locally? And we'll talk more about that when we get there. So let's look at this example to start off with. And this actually is an example from the textbook. This is number 10.4. This is 10.4, number 7. Just so you have a reference point. So here is our setup. We are given the following. The system of equations, differential equations, is dx1 dt is equal to negative 5x1 plus x1 times x2, and dx2 dt is equal to x2 minus 5x1 x2. How do we know these are nonlinear? Because we have x1 times x2, right? So to be linear, whether it's homogeneous or not, you just have, the only thing you can really have is a multiple of each of your variables. So like 4x1 plus 3x2 would be linear, or 2x1 plus 5x2 plus 7 would be linear. But as soon as you have something other than just a constant times a variable, it's nonlinear. And that x1 times x2 there, that's what's making this a nonlinear differential equation. If you graph this, it would not be a line. All right, so to find the equilibria, there's going to be plural typically. Just like back in the day, we're going to set the differential equation equal to 0, right? Just like in 17b, to find the equilibria, we're going to set the differential equation equal to 0. It's just that in this case, it's kind of more like finding the critical points of a function of two variables, because you can't just say that one equation has to equal 0. They both have to equal 0 for the same values of x1 and x2. So if we set these each equal to 0, well, now we're back thinking about finding critical points. So it's kind of like playing the game where you're trying to solve the one that's easier to solve first. These are pretty much the similar equations, so either one's fine to solve first. Let's work with this first one. I'm going to factor out an x1. Something cool. X1 times negative 5 plus x2 is equal to 0. So I'm either going to get x1 equal to 0 or x2 equal to 5. I stressed this before, I'm going to stress it again. 0, 5 isn't one of our equilibria. It is not making both derivatives equal to 0 at the same point. If you plug in 0 for x1 and 5 for x2 in the second equation, you're not going to get 0. So I'm going to plug in one of them. If I take this equation and plug in, say, x1 equal to 0, I'm going to get x2 minus 0 equal to 0, which means x2 is going to equal 0. So one of my equilibria, which I'm thinking of as a critical point, but that's not really the right terminology. One of my critical points is x1 hat, x2 hat equal to 0, 0. You guys see that okay? It looks okay. Doesn't look great from my perspective. The other one, we're going to set x2 equal to 5. So take this equation now, set x2 equal to 5. I guess I could have factored out an x2, but I don't really need, sure, why not? So set x2 equal to 5, I get 5 minus 5 times 5 is 25, x1 equal to 0. That's going to give me, so I'm saying x2 equal to 5 here. Notation's not great, James. I'm going to get 5 equal to 25 times x1, or x1 equal to 1/5. So my other equilibrium is x1 hat, x2 hat equal to 1/5 comma 5. And those are points that we can plug into both equations, and each equation would equal 0 at each of those 2 points. So these are our 2 equilibrium points, no longer just the origin. We're going to do a whole bunch of work right now that we're generally, unless asked to find the linearization, we're usually going to skip all this work and jump straight to just classifying the equilibria based on a thing we'll get to in a moment, which I don't want to give away the end. So we're going to linearize each of these differential equations around each of the equilibrium. What do I mean when I say linearize? Well, it's kind of like back in 17A where you have like a curve and you want to approximate it with a linear tangent line. Same idea. Really. And that's, I mean, really, there's kind of not a lot more to say other than the same idea. So as a reminder, just as a reminder, way back when, you probably don't need to write this down. I'm just going to remind you to linearize a function f of x at the point a comma f of a, just a lot of fancy words for finding the equation of the tangent line at the point a comma f of a, we would write or get that L of x, the linearization, is equal to f of a plus f prime of a times x minus a. You guys remember that a little bit? Which, if you want to view it as, you could think of this as, here's another way to look at it, just so you can all see it. This is like your y, this is like your y1, this is like your slope, this is like your x1. This is really just another way of saying y minus y1 equals your slope times x minus x1. Just finding the equation of the tangent line at a particular point. Okay. The deal here is, for these 2 differential equations, we're going to linearize both of them simultaneously. So usually what people do when you're doing this is they call the first one f and the second one g. So back up here, I'm going to call this equation f and this equation g. I'm going to write it down here too, so you don't have to write it. So here's what we've got. We have that f of x1 comma x2 is equal to negative 5x1 plus x1 x2, and g of x1 comma x2 is equal to x2 minus 5x1 x2. And we're going to linearize both of them. But when did we do this? Did we talk about, I forget. I'm trying to remember when we did linearizations of functions of 2 variables. I think we did it this quarter. I don't remember, to be honest. I think we did it this quarter, where there was an additional piece, right? Instead of just this, our linearization of a function of 2 variables was, sorry, I'm going to squeeze it in here. I know it's terrible. I hate it. I hate when instructors do this. Sorry. So for functions of 2 variables, the linearization was like L of x comma y was equal to f of x naught comma y naught plus the partial derivative with respect to x evaluated at x naught y naught times x minus x naught plus the partial with respect to y at x naught y naught times y minus y naught. Still the same idea, right? It's just the point you get when you plug in your point plus the derivative in the x direction times the difference in the x's plus the derivative of the y direction times the difference in the y's. We're just extending this linearization idea in another dimension. Okay, so now we're going to do this linearization for each of these functions. It's a little bit gnarly, but it's not that bad. So, yeah, let's do it the long way. So then we can see how nice it gets to be. So let's linearize f first. So for f, we can see that, and this is where the notation gets a little bit gross. We're taking partial derivatives with respect to x1 and x2. So our partial with respect to x1 is going to be negative 5 plus x2. And I actually don't want to plug in a point right now, and here's why. If I plug in a point, well, I have to pick which of my equilibria I'm going to plug in, whether it's 0, 0 or 1/5 comma 5. And I actually kind of want to leave my options open. So let's just actually leave it like this. So there's my partial with respect to x1. And then for x2, partial with respect to x2 is going to be 0 plus x1. Let me be, yeah. I know what I can do. I can be smart. So then if we're plugging in our equilibrium, we're going to just say, well, I'm going to plug in the x1 hat, x2 hat value. So my partial with respect to x1, and I know, so again, I'm kind of doing something that's terrible, but you'll forgive me. I'm plugging in my equilibrium, x1 hat, x2 hat. So I'm just going to change those to hats. Same deal here. X1 hat, x2 hat. So here's what we're saying. These are our slopes in the x1 direction and the x2 direction at whatever our equilibrium happens to be. I'm not going to write it out, but I'll just say if we plugged in 0, 0, our slopes would be -5 in the x1 direction and 0 in the x2 direction. And if we plugged in 1/5 5, we would get 0 in the x1 direction and 1/5 in the x2 direction. We're plugging in 1/5 for x1 and 5 for x2. Okay, so here's what the linearization is going to look like for f. Let me see if I can, yeah, what notation do I want to use here? Sure, I guess I'll write L sub f. My linearization for the function f of x1 comma x2 is going to look like, I'm literally just going to copy this formula, but make it look a little bit different. So it's going to be f of x naught y naught. Okay. What am I plugging into my function here? I'm plugging in my equilibrium. So if I plug in either equilibrium, whether it's 0, 0 or 1/5 5, the f part's gonna be equal to 0. So is the g part in the next step. So I'm just gonna write it down, but then I'm gonna point out if I plug in f of x1 hat, x2 hat, that automatically has to be equal to 0 because it's the equilibrium. It's where so it's where my function, which is the derivative, right? I know we've kind of divorced ourselves from that for a minute here, but as a reminder, we called this f, but it really was dx1 dt. And the second one was really dx2 dt. So it's where the derivative was equal to 0. Oh yeah, well then that should be equal to 0. Plus my derivative in the x1 direction. So that's going to be my -5 plus x2 hat multiplied by my x minus essentially my variable x1 minus the equilibrium point x1 hat. I fully admit this looks a bit gnarly. We're almost there though. I promise you it's going to get less gross. And then similarly, my fx2, which is going to be my 0 plus x1 hat, which I'm just going to write as x1 hat, times x2 minus x2 hat. Again, this is just my slope in the x direction, my slope in the y direction, multiplied by each variable minus its corresponding equilibrium value. And then we would do the same for g. I'm going to just, so I don't think we need, well, yeah, we do need to write it out. Let's do it the long way. Okay, so now for g, same sort of deal. Don't worry, I promise you it's going to get better. For g, taking the partials, my g x1 evaluated at x1 hat, x2 hat. Well, looking at g, the partial with respect to x1 is going to be 0 minus 5 times x2. It'd be -5 times x2, and then we're going to plug in x2 hat to turn that x2 into an x2 hat. That's kind of convenient notation. I can see now why someone might have picked it after all these years. And similarly, the partial of g with respect to x2 also evaluated at x1 hat, x2 hat, whatever that equilibrium happens to be. Well, let's see, it's going to be 1 minus 5x1. And then we're going to plug in x1, x2 hat to get 5x1 hat. So our linearization for the function g of our variables is going to be same sort of deal. It's going to be g evaluated at your equilibrium plus our slope in the x1 direction, which is going to be negative 5x2 hat times x1 minus x1 hat, plus our slope in the x2 direction, which is going to be negative 5x1 hat times x2 minus x2 hat. Looks pretty awful. It's about to look less awful. Because what we're going to do is we're actually going to write this as a matrix equation. So here's how we're actually going to write all this. Let's keep this all on page here. You guys can see that, yeah. So here's our linearization as a vector function. So really, I'm just going to take each of these equations and kind of put it together in one matrix. You might want to watch for a second. So it's going to be, oh, I should also point out that's 0, 2, right? G evaluated the equilibrium is also 0. So it's going to be 0, 0. I don't even need to write that really. Plus, okay, here's where the magic happens. This 2 by 2 matrix, which we'll fill in a second, multiplied by the vector x1 minus x1 hat, x2 minus x2 hat. That's a 2 by 1 vector. This is going to be a 2 by 2 matrix. So the 2 by 2 matrix is literally just all those coefficients. It's going to be negative 5 plus x2 hat, x1 hat, and then negative 5 x2 hat, negative 5 x1 hat. I feel like that seems, I feel like I missed something here. I want to make sure I'm not making a terrible mistake. I did miss something. Yeah, I missed something. Ooh, that should be a 1 minus 5x1 hat. No. Yeah. It should. Yeah, sorry, I missed the 1 there. Apologies. Which I wrote right there. Yeah, sorry about that. A 1 minus 5x1 hat. Or more generally, the linearization is equal to this 2 by 2 matrix, which is called the Jacobian. It's the matrix of partial derivatives. The partial, so in the first row, it's the partials of f. It's f with respect to x1, f with respect to x2. In the second row, it's the partials of g. G with respect to x1, g with respect to x2. Multiplied by x minus x1 hat. Sorry, x1 minus x1 hat, x2 minus x2 hat. That is your general linearization. And then what the idea is going to be is that 2 by 2 matrix, well, actually, I'll back up for a second there. Let me hold on for a minute before I say that. So let me pause for a second before we continue with this specific example and kind of do it for each equilibrium. Questions about anything I've said so far? Okay. So let's go ahead and write down the linearizations for each of our equilibria. And again, to do that, I'm really going to look back at actually this part right here. And I think we can fit in for 0, 0 right now. So for x1 hat, x2 hat equal to 0, 0. And I know he used some like epsilon notation, which is pretty typical. I wouldn't stress too much about that. It's whatever. But for this one, here's what we're going to get. We're going to get the linearization at x1 comma x2, or I should say of, right? Not at, is going to be 0, 0 plus, okay, here's our 2 by 2 matrix. We're plugging in 0 for each of the hats, negative 5, 0, 0, 1. Times x1 minus 0, x2 minus 0. And I suppose to make it even more explicit here, right? This is our F1, F2, which is really, sorry, our FG, which is just our dx1 dt, dx2 dt. This looks a whole lot like our typical derivative equals matrix times variable kind of situation. I know I wrote the derivative on the wrong side. You can live with that, right? Usually put it over here, it's okay. But we know how the solutions to a system like this work. In fact, this one's super extra easy because you already know the eigenvalues. In fact, this is like the easiest case ever because not only do we have a zero in one spot, we actually have a zero in both spots, meaning the eigenvalues are -5 and 1, and the eigenvectors are 1, 0, and 0, 1. Right? You can find them super easily. So what does this mean? Well, what it means is that locally around 0, 0, it looks like a saddle. So since our eigenvalues are +1 and -5, locally around 0, 0, we have a saddle. A better way to probably say that though, because usually you don't actually, I should be more careful with my language here. We usually don't say what kind of thing we have so much as whether it's stable or unstable. So I wouldn't say that we locally have, or I shouldn't say that we locally have a saddle. What I should say is that 0, 0 is locally unstable. That's a better thing to say. So 0, 0 is unstable. On the other hand, let's look at the other equilibrium we have. I'll try and write it a little bit more nicely here. So for x1 hat, x2 hat equal to 1/5 comma 5, our linearization L of x1 comma x2, which again I'll remind you is just dx1 dt, dx2 dt, also known as FG. And I'm writing way more things than I need to here just so that we can see kind of all the things we are calling this for a minute. FG is equal to the 2 by 2 matrix. Well, again, I'm just taking my point and plugging it into this 2 by 2 matrix. So I'm plugging in 1/5 for x1 and 5 for x2. The -5 plus 5 is 0. 1/5. -5 times x2 is going to be -25. And 1 minus 5 times 1/5 is going to be 0. Times x1, x2. That's my linearization. It's just giving me two equations, really. Oh, I made a mistake. Sorry. It should be x1 minus 1/5 and x2 minus 5. Sorry, that's terrible. Apologies. I'm going to write this one out, although normally I wouldn't, just so you can see the additional thing. So what this looks like here is it's going to be two equations, 0 times that plus 1/5 times that. So it's going to be 1/5 times x2 minus 5, which ends up equaling 1/5 x2 minus 1. And then -25 times x1 minus 1/5, which is going to equal plus 0, which is -25 x1 plus 5. I will point out this is a non-homogeneous system of differential equations because I have some constants at the end there. We've talked about that already. We know that those constants don't really matter all that much except that they change what the equilibrium is. We already know what the equilibrium is. We found it. It was -1/5, or sorry, 1/5 and 5. We know how to deal with a system like this, right? So based on our 2 by 2 matrix here, we have to find the eigenvalues, right? We can't just, or I should say, we don't have to find the eigenvalues, we have to determine the stability. So let's determine the stability of the equilibrium x1 hat, x2 hat equal to 1/5 comma 5. You could find the eigenvalues. That'd be a totally valid way of doing it. We could say, hey, determinant of a minus lambda I is equal to the determinant of negative lambda, 1/5, negative 25, negative lambda. That's a pretty easy one to deal with. That's going to be lambda squared minus 1/5 times negative 25. Wow, if I could write numbers maybe. Which is going to be lambda squared plus 5, which means we're going to get imaginary eigenvalues. We're going to get lambda squared equal to negative 5, lambda equal to plus or minus I root 5. Okay. Oh yeah, that's a good question, James. How do you answer this question? Maybe this second part doesn't have a good answer. Yeah. So I'd point out that in this situation, I don't know if you call this stable or unstable, to be perfectly frank. Because if we were thinking about what sort of thing we have, let me ask you first of all, spiral or node? Spiral. Okay, here's a not good question I'm going to ask anyway. Stable or unstable? Well, I actually didn't give you the right chop. Let me rephrase that. Stable, unstable, or neither? Neither, because there isn't a real part, right? If there was a negative number out front here, we'd say it was a stable spiral. If there was a positive number, it'd be unstable. This is a neutral spiral. And I don't really know if you classify that as stable or unstable. My guess would be unstable. I don't really know though. So the linearization here is kind of a pain, but it's actually not that big a pain. I just made it more of a hassle than I really needed to. So the real process is find the Jacobian. Let me back it up. So let me actually write it down. I try my best. Sometimes better than other times to sorry here, to write things down instead of just saying them. Sometimes I succeed, sometimes I don't. So I'm just trying to make sure I'm putting things in the right order here. Apologies. Okay, good. There we go. So what I was gonna say is typically to linearize a system of non-linear differential equations. There's a couple steps. I would say step one, find the equilibria, find all equilibria. Equilibria, sure. And there's probably more than one. There doesn't have to be, but there could be. There likely is. Two, find the Jacobian matrix. And I'll say a bit more here. So typically, when we do this, we imagine our first differential equation is F, our second differential equation is G. So we're usually imagining our first one as F equal to dx1 dt and G equal to dx2 dt. And then our Jacobian matrix is equal to the partial of f with respect to x1, the partial of f with respect to x2, the partial of g with respect to x1, the partial of g with respect to x2. I always remember it as f on top, g on the bottom, x1 in the first column, x2 in the second column. That's how I think about what I'm doing. And then step 3, well, yeah, sure, step 3. Your linearization is going to be, which you already kind of wrote down, I'm writing again, is the linearization as a function of x1 and x2 is equal to that Jacobian matrix with your equilibrium plugged in multiplied by the vector x1 minus x1 hat, x2 minus x2 hat. Again, x1 and x2 are variables. X1 hat and x2 hat are the values of the equilibrium. Wow, took a lot of time to do that. So let's look at another example. Yeah, I like this. This example is all right, I think. Yeah, cool. So usually the questions surrounding this are either, it's either an either or an and, are either to linearize and or classify the local stability / instability. Or I should say classify the stability for each equilibrium. So let's look at this next example, and we should be able to finish this. I don't think we're going to get quite as involved here. So here's another example of a system of nonlinear differential equations. We have dx1 dt equal to 3x1 minus x1 squared, which is really always terrible looking, minus x2. Terrible when you have a subscript and a superscript. This is why I would definitely choose to use x and y, but we usually don't. dx2 dt is equal to x1 minus x2. And I would recommend, whenever you see something that's nonlinear, call the first one f, call the second one g, write it down. Yeah, that one's f, that one's g. Do yourself a favor. Okay, let's find the equilibria. All right, let me ask you all, which equation looks less terrible? The first one or the second one? The second one. If we set the second one equal to 0, we know that x1 has to equal x2. Great, so all the equilibria are going to be like 3, 3, or 5, 5, or -7, -7, or whatever the values are, both coordinates are going to have to be the same. Let's plug that into the other one. So then the other one's going to be 3x1 minus x1 squared minus x1 equal to 0. Simplifying, that's going to be 2x1 minus x1 squared equal to 0. Factor out an x1, you get x1 times 2 minus x1 equal to 0. So we're either getting x1 equal to 0 or x1 equal to 2, meaning our equilibria are going to be either 0, 0 or 2, 2. Those are our two equilibria. Now let's find the Jacobian. And again, I would say you're going to find the general Jacobian, meaning as a function of x1 and x2, and then you're going to plug in each equilibria to then classify stability of that equilibria. So our Jacobian, again, reminding you, it's the partial of f with respect to x1, the partial of f with respect to x2 in the first row, and then in the second row, gx1, gx2. Let's see, so fx1 is going to be 3 minus 2x1. The 1. fx2 is going to be -1. gx1 is going to be 1. gx2 is going to be -1. Interestingly, there isn't going to be a place to plug in the value of x2. It's okay. Now, even though I'm not being asked to, I'm still going to find the linearizations. So usually the linearization is not super necessary, but it's still worth talking about. So the linearization, let's do 0, 0 first. Okay, so notably, the Jacobian at 0, 0, we're just going to plug in 0 for x1 and get 3, -1, 1, -1. So here's our linearization. What we're saying here is that our linearization of x1 comma x2 is just that matrix, 3, -1, 1, -1, times our variables x1, x2. What are we really saying with this? Here's what we're really saying. We are really saying that near, how near, who knows? Close enough. That near this equilibrium 0, 0, that if you look at this equation here, that our non-linear system can be approximated by the linear system represented by that matrix, which I'm going to write out, that dx1 dt is equal to 3x1 minus x2, and that, not surprisingly, dx2 dt, since it's already linear, is going to be 1x1 minus x2, which is what it already was, right? So here's what we're saying. Near the origin, this differential equation is oh my God, words, is linearly approximated by this equation, which might just look like I took away that part, but it's really because that function in this direction, that derivative is just zero anyway. So that's why that part's just going away. And then we can classify stability based on that. So is the origin stable at this point? Well, what's our matrix telling it is? Telling us it is. We can either find the eigenvalues or we can use the trace determinant method. Let's use trace determinant because it's usually what people do. So stability. The trace is, I should never find the trace first. That's like the wrongest choice, but it always feels like the right thing to do because it's the easier thing to find. The trace is 3 plus -1, which is 2. Which tells me that if it isn't a saddle, it's going to be unstable. Oh, there's a whole theorem about this. I totally forgot. There's a theorem in the book about like how you don't really need to look at, yeah, I'll say it in a minute here. And then the determinant is going to be -3, 3 times -1 minus -1 times 1, which is equal to -3 plus 1, which is -2. So if we were dealing with a linear system, we would say that we had an unstable node. Since it's a nonlinear system, we're just going to say it's unstable. At 0, 0. Or really, the words here, I'm failing you kind of. What we say is the equilibrium 0, 0 is locally unstable. So let me rephrase that. The equilibrium 0, 0 is locally unstable. And I believe the theorem says that so here's a theorem. The theorem says that if both the determinant and the trace are negative, then it's locally stable. And I think unstable otherwise. I'd have to double check the textbook for that. Unless it's in my notes right here. I don't see this. I don't see this in my notes right here. Just bad. But I'm fairly certain that's the case. Because if you think about, I made a mistake. Let me ask you all a question, which I know I should know the answer to better than you. But if the determinant's negative, what do we usually say we have? A saddle. And what do I usually say about a saddle? Is it stable or unstable? So I will point out, I've written the wrong thing here. Saddle we usually classify as being unstable. I wrote the wrong thing. I should have been saying the term. Well, oh wow, I made many mistakes here. Apologize. So, well, actually, kind of. So the mistake I made here was this should be the determinant being greater than 0. Right? If the determinant's greater than 0, then we don't have a saddle. Right? We're on the top half of our saddle spiral node graph kind of thing. And if the trace is negative, meaning we're on the left-hand side, we have stability. So what I should have really said here is, not only are we unstable because our trace is positive, we're also unstable because we have a saddle, which I messed up on before. Sorry, I made a mistake about getting numbers backwards. So very unstable here. We already said that, but we should have said it for more reasons. So if your determinant's positive and your trace is negative, then you can say it's locally stable. Or you can make the easier choice. Well, I would say you can make the mentally easier choice, but the computationally more difficult choice of finding the eigenvalues and then basing your answer based on whether the eigenvalues would give you something that you know is stable or you know is unstable. So if I had found the eigenvalues here, I would have gotten that my eigenvalues were either positive and real. Nope, I would have gotten one of each. Sorry, I would have gotten one positive, one negative. All right, my eigenvalue is doing one positive, one negative, and I would have known it was unstable because I know that would lead to a saddle-ish thing. Okay, let's do the other one. It's a little more interesting. Let's not lose this piece of paper here. So my other linearization at the point 2, 2 of the equilibrium 2, 2. So let's find the Jacobian there. I know the Jacobian's way back on the other page. The Jacobian at 2, 2, looking back at my matrix, I'm just changing the first entry, first column, first row. It's going to be 3 minus 4 instead of 3 minus 0. So that's going to be -1, -1, -1, -1. Right, just as a reminder, there's my Jacobian matrix. I'm just plugging in 2 for x1 instead of 0 for x1. Let's go ahead and write the linearization. So near 2, 2, our system is going to act like, now I'm going to be extra careful this time. L of x1, x2 is equal to our Jacobian, -1, -1, 1, -1, times x1 minus 2, x2 minus 2. Which if we multiply it out, which would approximate dx1 dt equal to -1 x1 plus 2 minus x2 plus 2, or dx1 dt equal to -x1 minus x2 plus 4. And similarly, dx2 dt would equal x1 minus 2 minus x1 minus x2 plus 2, which would just be dx2 dt equal to x1 minus x2. Again, it shouldn't be a surprise at all that dx2 dt didn't change at all from the original because it was already linear. So if you're linearizing something that's already linear, it shouldn't end up changing at all. So what we're saying here is that, where'd you go? Sorry, I keep going back to this page here. One moment. What we're saying now is that this differential equation near the point 2, 2 is approximated by the linear differential equation dx1 dt equals -1, -2, minus x2 plus 4. This is a good approximation of this differential equation at the point 2, 2. Kind of weird, but it makes a little bit of sense because if you plug in 2, 2, you get 0 for that and you get 0 for that. And then as long as you aren't too far away from 2, 2, the values of this will be close to the values of this. All right, let's wrap it up. We still have to classify. So we'll do this both ways. So stable or unstable? Well, let's find the determinant in the trace, and hopefully I'll do it right this time. The trace is equal to -1 minus -1, which is 0. That's lovely, just what I wanted. This is just what I wanted. No. And then the determinant is going to be 1 minus -1, which is 2. All right, we actually should know what this is, although it's been a minute. So our trace is 0, meaning we're not on the left or the right side of this thing. We're right in the middle. And the determinant is 0, meaning we're on the upper side. So we're definitely not a saddle. We're right in the middle, which means we're not an outward spiral or an inward spiral. We're again seeing this neutral spiral kind of thing. And unless I made a dumb mistake. No, I didn't. Did I? Did I not? Grant made a dumb mistake. I made a dumb mistake. Oh my God. Here's my dumb mistake. I apologize. So sometimes people make mistakes. Guys, forgive me. How do you find the trace of a matrix? You add. So what's my trace actually? God. So you get for saying I'm not going to make any mistakes this time. I'm going to be really careful. God. So this is stable. Our trace is negative. Our determinant is positive. Those are the two things that need to be true to have stability. Our trace is negative. Our determinant is positive. Stable. Now, I'll point out if your trace is negative and your determinant is positive, it either means, from an eigenvalue perspective, that either lambda 1 and lambda 2 are both negative, stable node, or it means they're imaginary and your eigenvalues are a plus or minus b times I, and the a part is negative. We don't have to determine which it is, just that it is one of those two things. Now, if you actually found the eigenvalues here, you get negative 1 minus lambda times negative 1 minus lambda minus negative 1 times 1 equal to 0. That's going to be lambda squared plus 2 lambda plus 1 is plus 2 equal to 0. And then you get lambda equal to negative 2 plus or minus the square root of 2 squared minus 4 times 2 is 4 minus 8, which is negative 4 all over 2. So our eigenvalues are negative 1 plus or minus I. So certainly stable spiral kind of territory here. Again, not that we would say we have a stable spiral, because it's just looking like that locally. We would say we have stability around 2, 2. In the last minute here, let's take a look and see what this looks like, just because I think I mean, you guys know this already. You know, I think it's worthwhile. Let's see what this looks like. So we have our graph here. Oh my gosh, maybe not. Sorry, I just stopped sharing. Apologies. I know it's 2. Just give me a minute, I promise. Maybe I don't promise. Problem is this stuff in the way. Oh my God. I can't there we go. Finally. Okay. I know you can't see what I'm doing, but trust me, things are in the way. Okay. There's my phase vector plotter. Cool. Moving over here. And our differential equations. I know it's been a minute since I said what they were. So going all the way back to the original equations, we have, God, where'd they go? They're way back over here. Here we go. So our equations were dx dt equal to 3 times x minus x squared minus y. And our second one is going to be x minus y. Super easy. Graph it. And we zoom. So, whoops, don't do that. Or do that. Sure. So if you look around 0, 0, you can kind of see the saddliness. If you look around 2, 2, you can see the stable spiraliness. So locally, that's what's happening. But over here, who knows what's happening, right? All kinds of crazy stuff. So, right, stable spiral, saddly thing, weirdness over here. And you can have systems that have 3, 4, 5, lots of equilibria that are all doing their own kind of thing, depending. So you get close enough to one point, you get kind of sucked in, or close-ish to one point, you get pushed away because it's unstable. It's kind of neat. But the Jacobian kind of tells you all about whether it's stable or not. And then there's some weird corner cases where you might get a trace equal to 0. So that's the idea. You look at this 2 by 2 Jacobian matrix and you determine stability based on the trace and determinant, really. And you should look in section 10.4. There is a theorem right before the problem start that says exactly the thing I said about if the trace is negative and the determinant is positive, you get stability near that equilibrium. All right. That's all I have to say. It's 2:02. I should stop talking.